we're going to keep on practicing a little with the appliance sort data set in using matrix notation to be able to represent regression problems. But we're going to go ahead and expand the idea to multiple linear regression now. Now, remember, the example that we had was using only advertising expenditures in hundreds of dollars as a predictor of sales revenues. And again, this is a 5 observation example, so it's only meant for you to understand the concepts. We placed the y vector, the y observations, the response variables, into a vector, a 5x1 vector, and generally this is called the y vector, the response vector. We also placed the variable X, which is advertising expenditures, into what we call the design matrix. Now, there is another term for this. This is also called the model matrix. So if you see both of these terms, these basically represent the same thing. But the idea is that we place a column of ones, and that column is meant to represent a y-intercept. And then we would add every column of predictors. So in this case, this would be the variable advertising. Okay? So having said that, let's go and expand this example now to more than one predictor. And one of the first things that I want to illustrate is the concept of multicollinearity. Multicollinearity basically means that the concept is basically illustrating when two or more predictors are very related. So we're going to just define it this way. We're going to say that there is more multicollinearity when two or more predictors let's say are very related. And very related, this is very subjective. So right now, we're just gonna come back to that later. What does that very means? But for now, let's just illustrate it with an example. So right now we have this variable advertising, which is one of the predictor of the sales. Let's suppose that we have another advertising predictor, and basically let's do it so that it is very related to the advertising expenditures. Let's call this advertising 2. Okay, and to build a model matrix, what we're going to do is that we're going to multiply this advertising times 2, and in order not to make it an exact relationship, let's add some noise. So in this advertising 2, instead of spending $100, we're just going to multiply that by 2 and say that we are going to spend 210. And again, we are just using 2.1 as the units. So instead of 4, we're going to say this is going to be 3.9. Instead of 6, we're going to call it 6.3. Instead of 8, let's say it's 7.9, and let's just say that this is 10, just to make it just that one to be perfectly 2 times that column. Now, what we would say is advertising 2 is almost the same as advertising. It's just multiplying that column by 2 and adding some noise. So the concept here is that there is multicollinearity when 2 or more predictors are very related. So in this case, we would expect that there are problems with multicollinearity in this particular example. And we will see what that causes in a couple of minutes. But one of the ways that we can determine if there is multicollinearity in the data is by just getting a scatter plot of the 2 predictors. So if you plot them against each other, you would have here, let's say, x1 plotted in the y-axis, and let's say that x2 is plotted here, you would find that these two predictors have sort of a linear relationship among themselves. And before, we used to look at the relationship that advertising had with the response. And if we had another predictor, we always want the relationship among that predictor and the response to be strong, but we don't want these two predictors, advertising and advertising 2, to be related among themselves. Because if you think of it this way, they both are conveying the same information in predicting the response. So in other words, the information that advertising is bringing into the model is contained in advertising 2. And the same thing for advertising 2. The information that it conveys to the model, that it helps in predicting our response, is also included in advertising. So a scatter plot of these two predictors is an important way to recognize whether, two predictors are too related. Of course, this is a visual way. You can always get correlations, covariances, and among these predictors as a way to just measure the relationship that they have among themselves. And again, we're talking about linear relationships here. Okay, so having said that, the problem that we run into when we have a design matrix or model matrix that has two columns that are too related is that when we build the X transpose X matrix, then the determinant of that particular matrix is going to be close to 0. And again, close will depend on the units of the problem. So it might mean that, let's say, 100 might be close to 0 in a specific problem, but in others it might not be. So it's problem dependent. So in other words, if you get the determinant of the X transpose X matrix, the idea is that that determinant will be close to 0. And if you remember from the concepts that we talked about, what happens is that when you get the inverse of that particular matrix, the X transpose X inverse, then what happens is that the elements of that X transpose X matrix are going to be divided by the determinant. And again, if you think about this, if the determinant is going to be close to 0, and you're sort of dividing some of these elements by something that is close to 0, then what you get is that X transpose X inverse will have some sort of bias into the way that it's calculated, as opposed to problems where that design matrix is has columns or predictors that are unrelated among themselves. So we'll come back to that. Just remember one thing. We are using that X transpose X inverse matrix in a variety of ways. First of all, in order to calculate the B vector, the parameter estimates, we always use X transpose X inverse X transpose Y. This is the way that we obtain the least squares parameter estimates. So these actually minimize SSC, but we are using X transpose X inverse in the calculation to get the parameter estimates. So if you have columns that are too related, the determinant is close to 0, X transpose inverse is going to be sort of affected by dividing each element by the determinant, then you will get some sort of variation on these parameter estimates that don't, that would not be there if these two columns were completely unrelated. So that's the first thing. The parameter estimates are affected. Okay. The second thing that is affected is the variance or the variability of these parameter estimates. In fact, the variance of the true beta vector, the true parameter vector, is going to be equal to sigma squared multiplied by these x transpose x inverse matrix. In other words, when we get this in the parameter estimates, this is going to be estimated by MSE multiplied by these x transpose x inverse matrix. Now, what I'm trying to say with this is that these is also affected. The variance of the parameter estimates is also going to be affected by having two columns be two related. And again, this is where the intuition from matrix notation helps us understand better a regression and a multiple linear regression output. And we can see better how multicollinearity affects every single one of these parameter estimates when there is specifically two columns that are two related among themselves. Now, the first thing that I will mention is that if you have a column that is an exact multiple or a linear combination of another column, then you will get sort of an error in some software telling you, well, this x transpose x inverse x transpose x matrix is not invertible. I mean, I can't get the inverse because the determinant is equal to 0. On the other hand, if the two columns are two related but not perfectly linear combinations, you will get an answer, but it is up to the analyst now to know that these parameter estimates and these variance estimates are affected by the fact that the determinant of the x transpose x matrix is close to 0. Again, we'll come back to that a little later, but for now, let's think of these matrix here, and we'll put this into code. And let me just make another example. Let's suppose that we have a second predictor, and that second predictor right now is going to be, so let's put the same values in there, and so that would be the columns of the y-intercept, and let's put the advertising in there just as it is. But let's just use as a predictor, let's use the month. Okay, the month. Let's say that this is the month the product was introduced. So we have month 1, 2, 3, and 4, 4 and 5. It is going to be related. So if we had this month as a predictor of sales revenue, what will happen in this case is that this variable is actually the same thing as this one. So what we're going to do in our example is check what happens when you put month and advertising expenditures both as predictors. So we'll see that we will get an error, and we will see what happens when we put it into the LM function. And again, so let's put it here in there. So this would be advertising, and this would be month. Okay, so in this case, we have 1, 2, 3, 4, and 5. So in that case, this is an exact multiple. So these two columns are exactly the same. So you will see in the when we go to our how that works and what is the errors that you would get. And then as a third option, we're going to see an example where there is another column that is completely unrelated to advertising as well, so that we can see the differences in the parameter estimates and the variances of those estimates. All right, so this is pretty much it. Let's switch now to some code.